All right. So what we are going about to discuss today is now dive into the first law of thermodynamics now. And everyone's, I hope at this point, I think you guys are ready. We have everything in the house right now. Okay. So let's recap what we did last time. Okay. So what we did was talking about a couple of things, actually, a few things that we are going to need them today. First, we discussed how to calculate the work from the perspective of, yeah, you did eating wrong, from the perspective of thermodynamics. All right. So that was the first one. And we, 2 lectures ago, we talked about what does it mean by heat. All right. And we said, okay, every time that you have objects or systems with a different temperatures in thermal contact, then eventually there will be some exchange. And those exchange, we express it in terms of heat. Oh, there was incoming call. Can you give me a second? Oh, that got in the Bluetooth or something. It's got in the way. Sorry, guys. 1 second. All right, it's just the package sending. So they work so well to try to call every single time. All right, guys. Okay, so we were talking about heat, and every time that you have two objects in thermal contact with, of course, if they are at different temperature, they're going to transfer energy. And the energy transfer due to the difference in temperature, we define it as heat. But the key point to take is this. These two, if you notice, these two have the same meaning. I mean, well, same meaning in the sense that they both trying to tell you about the energy transfer. All right. Okay. Pen's color is not so good, but it's there. Okay. Energy transfer. Yeah, makes sense. Work is energy transfer. When you try to push something, then you transfer the energy from you to the thing that you are pushing. Make sense? Heat is energy transfer. Every time that you have different temperature, something is moving, that thing is temperature, that is energy. All right. And here comes the thing that is changing is the energy itself. And we have been talking so much about the energy and the connections with the temperature. And the conclusion that we say was total energy of the system turns out to be is just temperature. All you need is just single indicator. How high is your temperature or how low is your temperature? That gives you the level or the degree of, I mean, the size of the total energy of the system. All right. And of course, just to make sure that we talk about a simple system at this point. All right. So the relationship between the temperature and the total energy of the system is so easy to calculate, especially we are dealing with ideal gas. So the key for the ideal gas is once you know the temperature, you know the total kinetic energy of that gas system. All right, cool. But then because we are talking about the transfer, is the energy transfer, is the energy transfer, is the energy transfer. All right, I repeated myself. There's nothing wrong with the video. All right. So when you say transfer, they are changing, they are transactions. So you are not going to be talking about just the amount of energy, but because there are some transactions going on, energy must change. Make sense, guys? So that's why we are going to link this to the change, delta, the change of the energy of the system. And that's it. Here comes the first law of thermodynamics, guys. All right. So what we are trying to do is we're going to introduce the, well, name. I mentioned it a couple of times already. The total kinetic energy of the system is going to be some numbers that get averaged because, of course, you cannot keep track of all of the movements. You cannot keep track of all the speed, the collisions, everything. So all you can do is just average them, right? And if you're gonna have to keep saying that, hey, talking about the oxygen molecule in this room, what is the average total kinetic energy of those gas? It's gonna be like a mouthful, okay? So what you are trying to say is going to be just a simple word, internal energy. Done. So the energy total of the system, we're gonna call them internal energies. Okay, sounds good. All right, we're gonna use U for that. So this is the reason why we use the U over here, that just to indicate that we're talking about the total energy of the system. And then we put the delta in the front, that is the change of the internal energy. All right, so here comes the question. Do we lose energy while the system is transferring? That's a very good question. You have two directions. You can lose or you can gain, depends on the direction of the energy transfer. If you want to transfer out from you, you lose energy. If the energy is being transferred to you, you gain some energy. All right, make sense? All right, so both way, the delta can be positive or negative. All right, second thing to keep in mind, last time we talking about changing from one state to another state. So let me call this I or an F. All right, you can call it 1 or 2, doesn't matter. We say that you can bring talk about the gas. So we talk about PV diagram. So when you have a PV diagram, you specify the state of the gas at point I. And then you want to move or you want to change, you want to, adjust the gas, put it into a final state F. All right, so that will be another dot in the PV diagram. But we discussed last time that the way that you can bring your gas system from I to F, there are like infinitely many ways that you can do it. And each time that you try to do, the area under the curve will tells you the amount of work need to be done going from I to F. You guys with me? Right, that's the area under the curve, right? Second thing, just to remind you what we were talking about. In this case, guys, just answer me briefly. Going from I to F, the work done by the system is positive or negative? All right. Positive or negative, guys, from this diagram. Very good. Thank you so much. All right.
Okay.
Very good. So that's what it is. Gas expands. So the gas performs the work itself. So the work done by the system is going to be positive. So good. All right, here we go. If I bring this, just like last time, I can bring it in so many ways. I can do it like this. So if I want to know what is the work done, I need to figure out the area under the curve. You guys with me? So as you can see, different paths give you different work. So that's why we call it a path dependence. Work is a path dependent. You need to know how you bring your gas from I to F for you to be able to determine the amount of work done during that process. With me? And you can guess, going from I to F with a different path, that's probably going to involve different kind of heat. Of course, you can do some heat. You can bring in the heat. You can, there's so many ways that you can manipulate with the heat. So what I'm trying to say is heat. Okay, where was that? Maybe that was a long time ago. All right, but don't need that. All right, so what I'm trying to say right now is W, the work done, and heat, the Q, these two are path dependent. You need to know exactly how you treat your system for you to be able to determine work and heat. However, energy, just like what you love it before, energy is good. All you care about is just the state of the system. You guys with me? Okay, one more time. If I have a mass traveling at the speed v, what is your kinetic energy, guys? If the mass is m, you guys say it's 1/2 mv squared, right? No problem.
Okay.
But have you ever asked, how can you bring the mass to the speed v? Yes or no? No, I don't care, right? Doesn't matter. As long as you have a mass with the speed v, all you can say is 1/2 mv squared is the energy of this mass. Same thing with the, I mean, if you want to talk about the potential energy, if I have an object at the height, let's say 1 meter from your reference, you can say, all right, the potential energy of this one is mg1. Do I have to ask like how you bring this mouse up to this point? I don't care. So that's the concept of the energy. The energy is good to, I mean, so easy to drop it, easy to use, very convenient to use. You don't even have to care about its history. So this is the reason why energy is path independent. And definitely it's going to work for our total kinetic energy of the gas, or we now name it internal energy. So as long as it's an energy, it's path independent. Isn't that cool? All right. So the good thing is internal energy is path independent. But we already said for the gas system, internal energy depends only on temperature. That's all we need. Give me the temperature, I can give you the internal energy. So from now on, whenever you have a temperature of a gas, you can calculate the internal energy of the gas right away. You guys with me? Without knowing the history of those gas, I don't care. All right. How do you warm it up? How you cool it down? I don't know. But as long as you are at, let's say 300 Kelvin, I can give you the total kinetic energy of those gas right away. And the formula for that is just this. Isn't that amazing? Yeah.
Wow.
But to me, this is amazing. I don't know if you feel like me or not, but it was crazy since we know that temperature gives you everything about the kinetic energy of those tiny, tiny microscopic molecules in the system already. So from now on, just give me the temperature. I can give you exactly what is going to be the total kinetic energy of the gas in the system. The formula is you just plug in the 3/2 in the front, okay? And you multiply by the nRT. The good thing is still look like an nRT. So that means feel free to replace this with the PV because it's an ideal gas. So instead of giving me the temperature, you can give me pressure and volume. I can also still be able to calculate the U anyway.
Okay.
Cool. All right. So that's it. 3 components: work, heat, internal energy. All right. The first 2 was path dependent. However, they both link with the energy. W and Q are energy transfer. Energy itself is path independent. So this is it, guys. First law of thermodynamics is waiting for you right here. All right. It's very logical. Follow me here. All right. I'm going to maybe talk a lot today, but once you get the concept of this one, you understand the terminologies and conventions. It's very, very logical. I don't know what to say. It's logical. As I said, it's like money. It's like, I don't know, it's finance or whatever. Okay, talk about this. Here we go. Follow me here. Now you have a gas system. So this is like a grand total like summary of everything that we have done in the past 3 lectures is right here. So you have a gas system in here. Oh, I don't need to do anything with it. It's already good in color. All right. So do you have a gas system in a movable piston container and everything is just like before? Here we go. Think of it this way. If you come in with heat, and we already knew the convention, positive heat means heat is being given to the system. So it's a heat flow into the system. That's a positive heat, right? And heat is the energy transfer, correct? So that means somebody transferred the energy to the system. So what should be the change of the energy? Of course, increase. So what I'm saying over here is, if you want to connect the delta U, the change of the internal energy of the system to the heat, it must be in the same direction, or mathematically it's going to be the same sign. Positive heat means positive change. Negative heat means somebody take out the energy from the system. So that means the system's supposed to have a negative change. So the delta is going to be negative. Yes. Yes.
Okay.
All right. So that's why I can say if heat is the only thing that try to change the energy of the system, I will have to put it in this way. With me? Is that simple? If heat is the only mean for the energy to transfer, whatever the amount of heat flowing in or out, that is going to be exactly the same as the change in the internal energy. Done. Bam.
Wow.
Now, second step, talk about work. All right. We already agree that the positive work is the work that is being done by the system. You guys with me? So think about me. I have my energy. I already like maybe ate breakfast or whatever last night dinner. I got some energy in me right now. And if I am doing some work right now, that means I have to spend my energy that I have already collect or whatever I store in my body. So if I perform work myself, that means the level of energy in me is supposed to drop. Yes. So that means if I'm doing the work, the delta, the change of the internal energy is going to be negative. It's opposite. All right. Are you hearing construction? Sorry. Okay. Whoa. All right. So let me know if there's the distractions, whatever noise and sound come in. Okay. All right. So the work done by me is going to be in opposite direction to the amount of energy that I have to change. If I'm doing some work, my energy is down. So the delta is going to be negative. So if the work is the only mean that I can transfer energy in and out, the change of my energy is going to be opposite sense to the amount of work done by me. You guys with me? Okay, one more time. If the work is being done on the system, we said that is a negative work done, but with the negative sign in the front, that means the energy change of the system is going to increase. I mean, in going to be positive. It's going to change in the positive direction. The total of everything is, of course, this system, you can exchange energy through both. Come on, man. All right. You can change the energy in both ways. You can do it thermally through heat, or you can do it mechanically through work. So I'm just going to combine them, but we already know heat has the same sense of directions as the energy change. Work is opposite. I just add them, and that's it, guys. This is the one that I'm highlighting right now. Congratulations, guys. That is the first law of thermodynamics. Woohoo! Isn't that cool? Would that system create sound? In that, is that sound that coming from the upper floors? All right. So that's what it is. Okay. Delta U is heat, same sign, minus W, the work done by the system. All right, here comes the sort of like annoying fact that you probably need to know just a little bit. For those of you that maybe read like thermodynamics in chemistry, maybe, or maybe some textbook in physics ourselves, sometimes the formula doesn't look like this, but the formula look, the formula look like that. Now, let me ask you this. Can you guess what's the difference between the two? I mean, the reason is I faced this kind of confusion before at the time of like first time studying thermodynamics. It's like, what? This text sort of like put the first law of thermodynamics as Q minus W. When I jump to another textbook, they say, hey, the delta U is Q plus W. And I'm just like, hey, like sigma F must be equal to MA. That was the law. How come the first law of thermodynamics, you can, you know, sum them up, or sometimes you want to subtract them? Like, what is going on here? Can you sort of guess what It's a difference between the two, or it's like one is incorrect or no, or it's like what kind of thing that is kind of like feeling funny right now at this point. What do you think? Oh, sorry. Oh, there's some answer. Thank you. It's just like just being sad right now. I just too quiet. All right. So the thing is, that is just the definition of the W. Some textbook, they talk about the W to be the work done by the external force. That's all. But what we are talking right now, we keep saying that, hey, guys, W in our case is always W of the system. So every time that you look at the first law of thermodynamics, and then you see a positive W in this expression right here, you can understand now that, oh, this is the external force work done. You guys with me? All right. So actually, they are the same thing. It depends on the perspective of the W that you want to stick with. Okay. But for us, it seems to me that it's more natural to think of the system all the time. I don't know. I don't know you like this or not. And this will sort of create some confusion for you guys as well, because maybe it's my bad that I decided to pick this direction. But if you read the reference text of this course, they, in that text, actually use the external work done. But to me, it sounds annoying. Okay, there are two ways that you can annoy with this first law of thermodynamics. You can annoy with the sign first. And I guess that author just seems like, I don't like the formula that has a negative sign in it. I want a formula that has a positive sign in it. So let's define W to be W of the external force. Then everything will be positive and it looks nice and cool and everything. So that's why the reference text will use the W to be the W of the external force. You guys with me now? All right. But for us, I think, to me, and then you will see from examples that we're going to go through today, it seems to me like it's more natural to think of the system first. So we're going to focus on the system and it's going to feel more natural. But given that you already understand what's the difference or what's the similarity between the W system and the W external, well, no big deal. I hope. All right. Yahoo! Oh, that's not a good effect. All right. Anyway. All right. Here we go. Let's practice is a qualitative examples right now at this point. The drawing shows a pressure volume graph in which a gas expands at constant pressure from A to B and then go from B to C at constant volume. All right. You can see from PV diagram. Complete the signs in the table below. This one is like a quiz-worthy problems. It's like quick, easy, give you like a few minutes to complete and then submit for some points. All right, we don't have quizzes. Okay. All right, guys, complete the sign. I'll give you a couple minutes. And I'll have some discussion about the PV diagram as well. It will be a lot of fun. I guarantee you. With calculus with no extra charge. It's kind of perfect. All right. Slowly first. For those of you that sort of like seeing this for the first time, it's going to look a little like, you know, what is going on here, but it will get better. All right. So let's go through together for like the first row, shall we? Yeah. From A to B, guys. They already gave you the delta U to be positive. All right, what we have to do is just determine the sign of the heat and the work done. Let's attack the easy one. Which one is the easy one? Is the area under the curve give you the work done. You guys with me? Okay, and supposed to be positive or negative, guys? Gas from A to B. 0, not yet. From A to B though. Very good, very good. A to B is still expanding, gas expanding. So actually this one is positive. Okay, nice. Okay, got it? Okay.
Okay.
Now, it's time for the first law of thermodynamics. Delta U equal to Q minus W. Yes. The delta U is positive. Okay, now you want the Q. The Q is going to be delta U plus W. Okay. However, the delta U is already positive. W is also positive. Then it's guaranteed that this is going to be positive. This is how you use your first law of thermodynamics to try to figure out the third unknown parameters here. All right. So there are only three parties in the play right now. All right, guys. B to C. B to C. Let's attack the easiest one, guys. B to C. Work done is, this one is like, is it like a drum roll or something? Like, oh, no, that's not good. All right. Very good. Very good. All right. Got that. So at least B to C is a constant. The work done is definitely 0. Cool. And that, once again, from the first law of thermodynamics, delta U equal to Q minus W. I'm going to keep writing this like million times. All right. But because the W is now gone, so easy. Delta U is just Q. But Q is already given to be positive. Delta U is definitely positive along with it. Not bad. Not bad.
Okay.
Try again, guys. One more time. I think you get a feeling what is going on. All right. Get a harder one here. Now the drawing shows a pressure versus volume plots for a 3-step process. All right. That's fine. A to B, B to C, but C back to A. So this one we can say is a cyclic process. All right. So it's sort of like everything come back to the original points. Now determine the signs of delta U, Q, W, I mean everything, of course, during changes from A to B, B to C, and C to A. All right, this is more challenging now because you are not given anything at all. Wow, this is going to be harder. All right, guys, this is definitely going to be a quiz, but it's just for fun. All right, I'm just going to write everything just like the table that we just saw before. So we're just going to start from the delta U. All right, let's follow this one. Okay, they're followed by the Q, by the W, and then we're just going to analyze from A to B, from B to C, and then from C back to A. All right, guys. Now this one is definitely harder because I'm not giving you anything anymore. You're supposed to be able to determine the sign of each term by yourself. All right, but it's still good that it's still qualitative examples right now. But later you're going to have to calculate. Right? But for now, it's still sort of like, you know, chilling right now at this point. All right, guys, I'll give you a couple minutes to think for the first. Let's handle each process one by one. Let's go from A to B first. Fill in the table. A is greater than B, work is positive. That's a good start. That is a good start. All right. So let me sort of give you like a guideline over here. There you go. There you go. All right, guys, think of this a few minutes and give me the full answer. Is that like negative, positive, negative, 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 positive, on and on, right? So there's supposed to be 3 signs. Put it in the chat right away. I still have to learn the sound effect right now. All right, if you still sort of like get stuck a little bit, don't worry, because there are some trick or techniques that you need to learn a little bit more to sort of like, you know, speed things up or give you a fuller picture of how to deal with this kind of process for the gas. All right, but if you can, you know, twist your brain a bit to, you know, come up with the way of figuring out, it will be great. But if not, don't worry, right? This is not easy. This is considered a complicated one. So everyone's still with me, yeah? It's like, okay, Dan, You just keep talking and then I'll grab something to eat. I think I'm guessing right now you are stuck at the delta U. I'm guessing. Because from the look of it, you might want to get to the Q, but Q seems to be the hardest or the most mysterious one because seems like Q depends on the other two. The easiest one that you can attack right now is the W, of course. You can do that right away because once again, it's just the area under the curve. So going from A to B, all you need to calculate for the W is just the area under the curve of trapezoid over here. But no matter what, we already agree, going from A to B is an expansion. So when gas expands, the W is definitely positive. You guys with me? That's one step. Now Q, I'm not so sure, but at least in your head, it's linked to the other two. And it's path dependent. So it's not going to be easy to calculate. So let's attack the delta U first. What do you think about the delta U, guys? How can we determine what is the direction of the delta U change? I mean, what is the U change? The change of the U is a delta U. Is there any signature or something that you can grab from the PV diagram that eventually give you the definite directions of the change of the U? And here comes the, well, I would say, I don't know if it's a trick or not, but I think this one will be very useful for those like chemists or biologists or whatever in the future, because I think from time to time, you're going to get back to the PV diagram, no matter what. All right, let me recall this one more time. PV equal to nRT. Let me put it like a light blue. And we all look at the PV diagram, right, guys? Here's the key. When is a PV diagram? This is Y, this is X. Let's say that if I have a constant temperature, if it's a constant temperature, my right-hand side will be all constant. You guys with me? N is fixed, R is constant, if the temperature is constant as well. So the right side of this equation will be fully constant. So that means this equation will turn into something like xy equal to z. You guys familiar with this form of the equation? What is the shape of this curve? Xy equal to z. Remember vaguely? No, not linear. The linear is going to be y, let me put briefly here, equal to mx plus b. That's the linear. Yep, y equal to 1 over x. What is the shape of y equal to 1 over x, guys? Does it ring any bell? So it turns out xy equal to constant. That means the product between x and y must be fixed. So if x is big, y must be small. If x is small, y must be big, right? They must be sort of compensating each other all the time. Does that make sense? So if you plot a curve of this one, is the curve that look like this. Remember that? And of course, if you remember back in the day, you must have the other side as well. I mean, x and y can be both negative, but for us, we don't have the negative side of this one, so we don't worry about that. But okay, just to draw it a little bit bigger, maybe it's too small. So this is what it is. So it's the curve that go like this. That's the xy equal to constant. I think there is a name for it. It's like a, like that orthogonal hyperbolic or something. There's some name for it. All right, but it's a hyperbolic curve, but it's being tilted 45 degrees. That's what it is. All right, but anyway, the easiest idea is it's a product that equate to a constant. So when x is big, y is small. When y is small, when x is small, y is big. So that means at one particular temperature, you must have this curve running, highlight in blue. Yes? So that means look at point A, guys. Because point A, I mean, it's on a PV diagram, there must be a temperature associated with it. But point A must be located on one of these PV equal to constant. You guys with me? Same thing with the point B. point B must have one temperature, and that temperature will be on another one of this curve. You guys with me? Same thing with C. The C is one temperature, so it must be on one of this hyperbolic curve. I mean, curve looks so bad, but that's what it is. But the reason that I'm trying to get you to this is because which one should have a higher temperature, guys? The higher lying curve or the lower lying curve? Everyone can guess. The bigger the constant, the curve will get up and up and up toward the sort of like a diagonal right? So it's sort of like is the higher the curve, the higher the temperature. So I can say this is going to be a high T, and it's going to get lower and lower and lower. So this is a lower T temperature. It's going down. And that's it. You guys get what I'm trying to get to now? Going from A to B, you are jumping from a lower temperature to a higher temperature. See that? So actually, I have a name for you guys. We call this an isotherm. It's an isothermal line. It's the line or it's the curve that showcases the constant temperature line. So that means the A is lying at the lower isotherm. I mean, lower temperature isotherm. So that means jumping from A to B, you're jumping from a lower isotherm curve to a higher one. And that means you increase in temperature. But we already learned that the temperature increases means energy increases. And that's it. So going from A to B is going to be a positive change in the internal energy because you are at a higher temperature after this path, going from A to B. B is at higher temperature than at A. All right, got it? Once you got this one, then you can track down the Q using, once again, first law of thermodynamics. Q is just delta U plus W. W is positive, delta U is positive. You guarantee that Q must be positive as well. Yay, all right.
Okay.
Cool. All right, guys, try B to C using the diagram that I'm drawing right now. So it looks complete now. You have all the tools and techniques. You understand the PV diagram. You see the connection with the PV equal to nRT. And with that, you can draw an isotherm at any temperature. And you use that to determine the temperature change. And that will lead you to the change of the internal energy.
Okay.
All right, guys, B to C. Go ahead. Fill those signs. Cheers for that first row over there. Positive, positive, positive. All right, guys, B to C. Attack the easiest one first, guys. B to C is still expanding. Yeah? Positive, work done. Okay. Now delta U. Delta U is jumping down because you're going from B to C. See, you can jump from a higher isotherm to a lower one. So the delta T is negative. I mean, the delta T is negative. Lower temperature must be delta U is also negative. Yes. All right. And once again, using the first law of thermodynamics, Q equal to delta U plus W. The delta U is negative plus W is positive. So this one you probably, well, not so sure. So let me put like depends, because this one you have to really calculate the value of the W and the delta U, which one will win, right? So the winner one will take the sign along with it. All right. So there's a question comes in. Can I just assume that increase in pressure equal to more? No. I would say no. All right. So this is the complicated one. The reason is because don't forget now, thermodynamics try to connect more than two variables or parameters all the time. Have you noticed that? See? So your friend is asking, does it mean all the time that the pressure higher means higher in temperature? You left out the volume change. So that's why I would say I have no clue. I wouldn't say it's not possible. or it's not true, but it can be yes, it can be no. Depends on the third parameters, the volume. You need the P, you need the V, and you need the T. So if you're just talking about the P and the T, that's not good. It's incomplete scenario. It's incomplete information. Okay, cool. All right. Oh, that's one comment. That's for the third one, I hope. Like plus, minus, no clue. Is that what it is? All right, try that. C back to A, guys. C back to A. The easiest one to attack is, once again, C back to A is a contraction. Yeah, so it's in a contraction. You know that is the work done by the system is going to be negative. Sure, this one. And from the given isotherm that I drew over there, C back to A seems like you're jumping from higher isotherm to an even lower one. So the delta U is supposed to be negative along with the temperature reduced. Yes? And that's it. Use the first law of thermodynamics one more time. Okay, W is negative, so it's guaranteed that this one is going to be negative. Done. That's complete the whole table right here. And I hope it seems like this is a good starting point for you to be able to jump right into next step. Next time we see this kind of question, you should be able to even calculate. Yeah. We need quantitative answers, right? This one is just sign. But I hope this give you enough time to sort of sink in and then try to understand what is about to happen. Is it good? All right. I hope it's all right.
Okay.
Okay. All right. All right, guys. So I'm not sure if I spell your name, pronounce your name correctly. Post so what? Yeah. So it's supposed to be negative, no clue, and positive for that B to C. You agree with that? All right. Okay. All right. Yeah. Okay. All right.
Okay.
Keep going. All right. Getting more real, guys. This is it. Now I'm asking you to find out, even though it's not numbers just yet, but you need to do a quantitative analysis now. A system undergoes a cyclic process as shown. Find the change in internal energy at the end of each cycle. So we assume that one cycle is A, B, C, D back to A. That's one complete cycle. And part B, find the total work done in one cycle. And C, find the heat transferred into the system. So now they care just a complete cycle. They want to know, hey, what happens after each cycle? All right, let's start from A first, guys. Part A. What is the change in internal energy in the end of each loop? Come on, man. All right, let's finish this problems and then we take a break. Sounds good? All right, there's some motivation here. All right, guys. Part A. Find the change in internal energy. I'll give you a clue right here. I don't know if this is a clue or not. All right, let's start here. Cycle, complete cycle. What is the change of the energy? Okay. That's some answer right here. Very good. All right.
Okay.
Yeah, because whatever you do, you come back to the original position. So that means think in terms of temperature, you are at the exact same starting temperature, right? No change. Energy does not change when the system is exactly at the same state. Very good. Perfect. B, guys. What about the total work done in one cycle? All right, this is a good one. All right, guys, try it. Zero. Wait a second. All right. That's too fast, man. That's too quick. All right. So that's not good. If B is 0, then C is definitely going to be 0. Yes, very good. It's going to be W from A to B and C to D. Very good. Very good.
Okay.
Right? Because you guys know that from B to C, you're not going to get any contribution to the work. D back to A, you don't get nothing. So the only two parts that is going to contribute to the net work done for this cycle is going to be from horizontal lines, A to B and C back to D. Give me the final answer. All right, so that's good start. So I think what you need to calculate is what is the work done from A to B and what is the work done from C back to D. And once you want that, you want the net. It's just going to be the sum of those work. Okay? That's the idea. All right, how much is the work done from A to B, guys? You guys say, Bachan, that's easy because it's going to be just the area under the curve from A to B. And that is exactly correct. There you go. So all you need to do is just figure out the height and the width of that rectangle in blue right there. All right. And then you guys should be able to fill in this easily, but it's just the width times the height. And it's going to be, all right, let's do the P1. That's the height. And the width is going to be V2 minus V1. So this is exactly what we did last time through the integral, but we don't need to integrate anything because the pressure is constant. Remember that, right? All right, now D back to A. For the D back to A, it's going to be the magnitude of this area right here that you need to calculate. That is the amount of work done. And once again, you can do P2. And then if you wanted just to calculate the area, you can take V2 minus V1. You guys with me? You get the area. But the kicker is, don't forget, C back to A is a compression of the gas. So the work done by the gas is supposed to be negative. You guys with me now? All right. Or if you can recall what we did last lecture, it's going to be P delta V, right? P times the change of the volume. So it's going to be V final minus V initial. So negative sign is automatically included here. All right. So at the end, all you need to do is just sum those two results. You get the net work done. But you can see from the figure over here, you started out with the blue area. And then at the orange shaded area, you sort of like get the negative of those areas. So it's like you have the blue and then you subtract out the orange. So what should you get at the end? Yeah, it turned out every cyclic process, the work done by that process is just the area enclosed by that loop, cyclic process and everything. Yeah, got that? All right, and that's it. So I can say, okay, then I can take the blue, subtract out the orange, and then I'll get the green. So from that, results. And from now on, next time, you can probably say, well, Ajahn, the net work done is going to be the width times the height of that cycle. So over here, the width is, the height first, P1 minus P2. That is going to be your height right here. And the width is going to be V2 minus V1. But here is another point that I want to make just to make sure that you guys understand the sign correctly. Here. This one is a clockwise process. When you have a clockwise process, the area in blue is positive. The area in orange is negative. So that's why your net result stay positive. You guys will see that, right? But if you have an opposite process that try to go counterclockwise, then everything will be reversed. Think of this process over here. If you want to go backward, the blue will be negative work done and the orange will be a positive work done. The net green will be negative work done. Okay, got that? So the direction of the path give you the sense of direction of the energy flow all the time. That's why sign is very important in thermodynamics, because everything is path dependent for the work and the heat. So you just have to be sort of like, be careful with sign all the time. Okay, got that? Okay, so I think part B is clear. That's good. Now the last one, what about the heats, guys? For each cycle. And this is the part that you say, Bachan, this is the easiest because we start from the first law of thermodynamics, delta U equal to Q minus W. So the heat is delta U plus W, but the delta U you already found out from part A to be 0. So that's it. So what you're saying over here is for this particular cycle, actually any closed cycle, the Q must be equal to W because any cyclic process, there's no delta U. Delta U is 0. So whatever the result that you got here, that must be the amount of heat. All right, but does that make sense to you guys? Well, yeah, Ajahn. I am a system. At the end of the cycle, I am having exact same energy in me. But it turns out during that time, I perform work this much. I am, let's say I lift the weights, doing something, I don't know, whatever going on. But I keep my energy fixed. I'm not changing my own energy. What does it mean? I must steal some energy. That's heat. I need heat to get into me, but then I use that energy through heat to perform the work without adjusting my energy. See, that's first law of thermodynamics. It's all about accounting, right? Okay, but the currency that we are using right now is energy. So you can think of energy as like a currency right now. It's like joule. How many joule you sort of like, take along with you today in your pockets? Something like that. All right, guys. So let's take a quick break right here. It doesn't have to be quick. It's a break. All right. And then I'll take, let's meet up at 11:10. Sounds good. All right. Let's do like 15 minutes break. And so, but I think you get some idea. Yeah. Yeah.
Probably on the break. But, what if the cycle, the shape of the cycle is like infinitely
the triangle?
long? No, not triangle, but like a fractal. A fractal that can have infinitely long length, but a finite area.
Oh, the fractal. Fractal, yeah. You mean the fractal in nonlinear stuff, right?
Yeah.
Well, I would say that's probably not gonna be something related to thermodynamics right now. Continue what we were talking. All right, so we will have a chance to do more now with the different kind of processes. Right? And there are main processes that we would like to be able to analyze, and it's quite straightforward to analyze, and the known results is going to be very useful later to do something with the thermodynamics applications. All right, so we are going to focus on the main 4 processes today. All right, and you guys will feel quite okay. At least 3 of them. All right, and once we give you a good introductions of this one, I think you kind of like, okay, I think they have something that can be applied. And next time we'll dive into like a lot of calculations. All right, so it's gonna be like, sit back and relax and try to look at these 4 processes all together. All right, but anyway, calculus is coming. All right, with no extra charge, is coming soon. All right, so these 4 processes I'm talking about are, first is a constant volume process. All right, they might have a name like Isoboric, but usually it's just straightforward to just say it's a constant volume process. And you guys already have seen this a couple of times before. It's just a process that represented in a PV diagram as a vertical line. Done. All right, and the good thing about this one is what? Work done is 0. Once the work done is 0, you guys, first law of thermodynamics. Delta U equal to Q minus W. W is gone. Done. Something like this. Isn't that fun? Second one, isobaric. So this one is an isobar. So this means the bar is constant. The bar means pressure. So it's a constant pressure process. You guys have seen this as well. It's the PV diagram curve that is flat, horizontally flat. So in that case, the easiest one to attack is the area under that curve is in the form of a rectangle. You can calculate this very easily using the width times the length. Okay, so that is your W. And in this particular curve over here is expansions of the gas. So everyone knows the work done by the gas is going to be positive. So for this one, W is positive, P times delta V. Cool. But the thing about this one is you have delta U equal to Q minus W. For the isobaric process, all three terms in the first law of thermodynamics are non-zero. So, all right, that's a fine, right? So we'll figure out later what is going on. Number 3 is an isothermal process. As the name can probably suggest, is the constant temperature process. And we already learned about what? Yeah, isotherm. Every temperature can sort of like trace an hyperbolic curve, right? We just saw that xy equal to constant. So that is perfect. So that means every time you look at an isothermal process, it must be on one of the isotherm. You kind of got that?
Okay.
Yeah. So that means an isothermal process will be the process that riding on a single isotherm. Yeah. Constant temperature force you to be just on this particular one isotherm. You cannot get out of this. And the good thing about this one is because the temperature is being fixed. Can you guess what is supposed to happen? Temperature is constant. Very good. Delta U is definitely is gone. No temperature change on this isothermal curve. So from the first law of thermodynamics, you're going to get 0 equal to Q minus W because delta U is gone. And this is the one that you just saw in the previous exercise in the cyclic process, that when you have a full cycle of the process, you get back to the original position, delta U is 0. So when the delta U is 0, Q equal to W. All right, but anyway, for this one, it's not a like cyclic process or anything, but just it's a process that has no temperature change. So during this process, amount of heat involved in this process must be exactly the same as the work done by that gas right there. So that means if you can figure out the area under the curve over here, the amount of work done, which is the same as the area under the curve, will be exactly equal to the heat need to flow during this process. All right, cool.
Okay.
The last one is something we call adiabatic process. All right, this one is the easiest in terms of the agreement of, right, okay, what we're going to do here is we're going to allow no heat transfer. For example, you might, insulate everything. Your container is, have a wall, big wall, or vacuum wall. You don't allow heat to exchange, or maybe some process that happens so quickly that heat has no time to transfer, things like that. So this one is the Q equal to 0 process. Okay, and we will learn the shape of this adiabatic curve toward the end of today's lecture. All right, so from here, delta U equal to Q minus W, and because Q is 0, that's it. Delta U is equal to negative of the work done. So if you have a way to figure out the W, if you have a way to figure out the area under the curve, that would signify the amount of the change of the internal energy. All right, so these are the 4 that we are going to sort of dive deeper into understanding how to calculate this. All right, let's start from the easiest one, guys. Constant volume process. This one, the reason I say is the easiest of all because, not delta W. W is 0. All right. First law of thermodynamics says delta U must be just the heat. And here comes something new of the day. All right. It's new because, well, it's new in the sense that I'm going to introduce some new parameter or, things that you need later. Actually, this is the heat. This is a delta U, right? But we just said today that the U of an ideal gas can be written as 3/2 nRT. We just learned that. And because we need the delta, and from the look on the right, you can see that there's nothing to delta with except the T. And we just already agree that the only way that you can change the internal energy of the gas is by changing the temperature. So that is, yeah, delta U is going to be 3/2 NR delta T.
Okay.
Now, let me rearrange this term just a little bit. Make it look like this. I put the N in the front, put the 3/2 R in the middle, and I leave the delta T at the end, just like before. But then because this particular process, this delta U is just exactly the Q. Do you notice something here? I'm trying to write down the form of the Q in terms of here, N something delta T. Delta T is equal to Q. Can you compare something with Q equal to MC delta T? Does it, yeah, the shape of the equation, does it look the same? Very good.
Okay.
So if that is the case, actually, I can interpret this formula in the same way as before. Instead of so there's some difference, of course. Instead of talking about the mass in kilogram, I'm going to talk about the gas in mole. Okay, that's one idea. Delta T will not change. That is fine. That's in Kelvin. And whatever in the middle, that's what I'm going to interpret as specific heat. You got that? So at this point, the 3R over 2 here can be thought of as specific heat. But instead of having a specific heat per kilogram, you just have the specific heat per mole. But is the formula that has the same shape as the Q equal to MC delta T. So what I can say is right now, if I rearrange this one, I can name this to be my specific heat. But because this is the specific heat that happens in the constant volume process, let me put the subscript V to it. Then I can re-express my Q in terms of the N C sub V delta T. Just leave it here, but this is good. It's always true. Every time that you bring a gas, an ideal gas, through a constant volume process, you can always be able to find out what is the amount of heat flow during this process by using NCV delta T all the time. And we know even better now that C is 3/2 R. Cool. Is it good?
Okay.
All right. That's done for the first process. All right. It's right now is like information flowing through your brain right now. All right. Second one, try the isobaric process. It's a constant pressure process. And we can calculate the work done very easily by looking at that rectangle over there. It's PV final minus V initial, or we can just say briefly, it's just P delta V. Cool? All right. Now, from the first law of thermodynamics, delta U equal to Q minus W. So all three terms are non-zero. But then I'm going to re-express to figure out the heat, because now I think you get a feeling that the heat is the one that has to rely on the work done and the delta U, right? So heat is going to be delta U plus W. But then the delta U is always fixed. It's 3/2 NR delta T. That's always the case for the ideal gas. The W you just got up here is a P delta V. Here we go. Plus P V final minus V initial. You start seeing something that we said that we can always use PV equal to nRT all the time from the gas equation. So that means I can rearrange this one to be nRT final. You guys with me? And then I can do PV final to be nRT initial. So far, so good. So that means this equation can look like 3/2 NR delta T plus NR delta T. So that last portion NR delta T came from P delta V. Of course, it has to be. And then I sum them up into 5/2 NR delta T and rearrange just like before. Put the N first, 5/2 in the middle, followed by the delta T. Do you notice something now? So that means I can say the heat during this isobaric process can be written in terms of the N, specific heat per mole, delta T again. And what else can I do? Except just call this specific heat in the process that having constant pressure.
Okay.
Yeah. So for the constant pressure process, I have another expression for it is NCP delta T. And I will review later. Why do we need this C sub V, C sub P? Like, Ajahn, why do we care so much about this? We need it later. Otherwise, then I won't trouble you guys with the introductions of these two terms. All right. But for now, that is it. Okay, I can deal with this. All right. But however, if you don't care so much about the formula, I mean, it's all about first law of thermodynamics right here and just calculating the work, which we know how to do it now. Okay.
Okay.
All right. I don't know you guys okay or not. I'm okay with my sound effects right now. All right. Next. Keep going. All right. So far, so good. 2 down. 3. The third process is isothermal. Isothermal is good. Delta U is gone. Heat is equal to work. Now is your turn. Can you calculate the work done by the gas, which is, of course, just the area under the curve? I'll give you a couple minutes head start. Find me the work done during the isothermal process. Wow. And yes, whatever you're thinking is correct. We need calculus. Why? No, that's not supposed to be. Oh, that's bad either. All right. Okay. It's supposed to be. Yahoo! All right, here we go. We need calculus right here. But how to find that? Okay, I'll show you right now. So to apply calculus for the work done, before we didn't really need to do a real integral, but now it's pretty much quite real. From the definition of the work done, it's just an integral of P dV. Last time, P is constant, you pull it out, everything's simple, but now you cannot because P is a function of V right now. What kind of function is that? PV equal to nRT, but nRT is just constant. You guys feel this one to be not too bad. So that means P is just inversely proportional to the volume. And that is already a function of volume. P as a function of volume. So I'm just going to use that function of P written in terms of the volume V, plug it in here. Can you see now what is about to happen? Yeah. And then all I'm doing, I'm trying to start from initial point to the final point. So I'm going to go from initial volume to the final volume. Cool. That's not bad. That's not bad. So far, so good. And then whatever constants, I can pull it out. What is not, I need to do the integration. So nRT, those are constants. I'm left with just 1 over V dV from V sub I to V sub F. Good. You guys finalize this, please. Yeah, for those of you that don't want to do it yourself, the answer is going to be this one. All right. nRT. Oh, sorry, ice is in my mouth. 1 over V dV. I forgot how to calculate. All right. The integral of 1 over V. Okay, let me remind you what we have. 1 over X dx is log of X. All right. You always need to plus some constant there. That's what we need for this one. Does that ring any bell? All right. So 1 over V dV will give you log of V. And do you put the lower limit, upper limit right there? Okay. All right. And of course, you substitute the upper limit and lower limits there. So it's going to be log of V final minus log of V initial, and subtraction of two logs, it's just a log of the ratio. So that's why that leads to there. Done. So that's it. So that gives you the area under the curve. And as you can see, the mathematics will take care of the sign itself. Yeah, because you have the initial, the lower limit, that's initial state. You integrate up to the final volume. If the initial volume is smaller than the final volume, your log will be positive because V2 is bigger than V1 or V final is larger than V sub I. Then you have a positive numbers at the end. So the work done is automatically positive.
Okay.
On the other hand, if you want to do the contraction of the gas, then the V final will be smaller and you have a log of something less than 1. So you're going to get a negative number at the end. So see, everything is automatic. All right. You know, I can't do the derivative. That's good because right now we're doing integral. All right. So you cannot do derivative. I think it's fine at this point. Okay. All right. But anyway, don't worry, guys, because why? It's always like this. It's always like this. You don't need to do calculus anymore because we do it once, we do it here, and we got the result right there. I blow it up for you. So from now on, whenever you have an isothermal process, you can actually just use this expression right there. Yeah. All right. Or there's a comment there. What even is calculus anymore? The curve. Yeah. But hey, wait for it. I will have like maybe toward like week 9, 10 or something. I will show you vector calculus. All right. With no extra charge. That's going to be a lot of fun. So just now is like, you know, ease you guys into physics a little bit. All right. But anyway, so for the isothermal process, you can use this. Yeah, a lot of fun. I guarantee you. All right, here we go. So that's good. That was the isothermal process. You know the W, and this W will be automatically equal to the heat. Done. Because delta U is no change. Cool. All right, last one, guys, is the adiabatic process. The good thing about this one is, well, we don't want to verify the formula. We used to do it. When I say I did it several years ago, and there was like it got boost on. Wow, no, you guys don't want to do proof or verification or anything. So I'm just gonna quote the result right away. But the good thing about this process is it's no heat transfer. Q is 0, right? You do whatever you do. You seal it, you vacuum it, you insulate it, whatever you do not allow heat to exchange. So when there's no heat exchange, Q is 0. The first law of thermodynamics reduced down to just this. Okay? Now here comes the thing, Ajahn, do I need to calculate W through the calculus again? Well, I don't want to deal with this anymore. I kind of know that you don't want to do this. And it turns out we don't really need to do that. The reason is because it's already automatically linked to the delta U, which is easier to calculate. You guys with me? So back in here, the reason we need to calculate the area under the curve because we have no way to figure out Q easily. And from today's experience, Q is the last thing that we want to calculate. Have you noticed that? Usually we try to get to the W first, if possible, the U, because it's easy. And then Q is sort of like Q comes last because it seems like Q depends on the other two. Same thing over here. Yeah, but now Q is gone. So you have two choices. It's either U or the W. And in our case, it seems like U is even easier than the W because U depends only on temperature. And then the temperature links to the pressure and volume through equation of state. So that's why, don't worry, we will not try to calculate the area under the curve. Instead, we pay our attention to the delta U and then try to figure out maybe the change of the temperature on and on. However, we still need to get this curve. This curve is weird. Okay. And this curve follow extra rules for adiabatic curve. And that rule is this one. No proof. Yeah. So we don't want to prove it, but this is good. This is an extra requirement for a gas to follow an adiabatic path. That's what you have. Okay. So you just agree with us that is PV to the gamma is going to be always constant. So that means as long as you stay on this adiabatic curve, no matter which point you take, P times V to the gamma, they are all the same. So this is the reason why you can write it down as this equation right here. P1 V1 to the gamma, or you can go PI VI to the gamma is going to always equal to PF VF to the gamma or P2 V2 to the gamma. So this is an extra condition for adiabatic curve. The only thing that I need to answer you guys is what the heck is gamma, right? It turns out, and you see now, it's good. I mean, it's just a fixed ratio between the C sub P and C sub V that we already introduced. So that means as long as you are dealing with a monatomic atoms that you already knew exactly, this is a 5½ R. This is a 3½ R. Yeah, you saw that before at the time of the introducing the isothermal process. I'm sorry, the constant volume process and the constant pressure process. So, isn't that cool? For monatomic atoms, get alpha is fixed, 5/3, 1.67 approximately. So that's it, guys. If you sort of okay to apply this equation, and then you can combine it with the PV equal to nRT at all time. This is always work. So you just sort of like combine these two, and then you can manipulate this into something else that you want. For example, instead of linking between the pressure and the volume, I can turn this into the temperature and the volume, whatever you like. And then you just read the information off from the PV diagram. And once you get the temperature change, come back here, and then you should be able to calculate the W through that one. Okay, that's just an idea. All right, but don't worry that I'm not going to ask you to do any crazy calculus or anything in this particular type of process. But one question though that I want to ask you, do you understand the curve of the adiabatic one? This is serious. Delta U equal to negative W lead you to this orange curve that's named adiabatic curve or adiabatic process. Can you tell me how and why or what is going on? Why the curve look like this? All right, the answer is not bad. You guys knows how to analyze this. Okay, here, sort of like go along with me here. Let's say I am starting here. That's my initial point is right there. I would like to, in this case, compress the gas to F. You guys with me, yeah, so far? But now, what I want to compress is I want to compress in an adiabatic mode. So it's mean I'm compressing the gas without exchanging any gas. Exchanging any heat. Okay, so you can imagine this one, Ajahn, in a real world application, what kind of this is going to be is actually think of like a heat that is flowing in and out in the car engine. In your car engine, you have to sort of like have a cylinder moving the piston up and down and combust the gas, right? And then you turn the wheel and other stuff from that combustion. But the idea is when you compress the gas down, that process is fast. You might be able to say like, hey, it's fast enough to assume that the heat doesn't have enough time to exchange. And then you treat that compression of the gas in the cylinder in the car engine to be adiabatic process. That's one example of application. All right. But in reality, of course, it's more complicated than that. But as long as you agree that, hey, assume that there's no heat exchange, this is a compression that is going to happen. However, look at this equation here, guys. Let me use different color to emphasize. Because it's an adiabatic process, the delta U, the change of the internal energy, is negative of the work done. Okay, follow me here. I'm starting right here. I'm compressing the gas down here. I mean, right now, because we don't know what kind of curve it's supposed to be, right? So this means I'm going to compress the gas down to a smaller volume. Let's say I'm jumping from V initial to a little bit smaller. During this process, what is the work done sign? Is it positive or negative? Positive or negative? All right, I answered. Oh, thank you. It's supposed to be negative change, right? Because you're going to a lower volume. So during this process, the work done is negative. But hey, see this? From the adiabatic process, delta U is negative of the work done. So that means this during this tiny process over here, it will lead you to positive delta U. You guys with me now? But when we already talk about the delta U as a positive, that's this one lead to what? Lead to positive temperature change. You guys with me? But when you say, hey, you have a positive temperature change, this means is the jump up. You have to change your isotherm line. So look at this. You're starting from that blue line. You compress the gas adiabatically. It turns out the temperature has to jump up. When I say jump up, it means you have to jump from one isothermal line to another isothermal line. So that's why the curve will tend to go steeper than just on the isothermal line itself. So that's why the curve jump up. And then you have to think about this in a continuous way. So that's why during the compression process, the curve will keep jump up, mean you skipping to a higher isotherm, higher isotherm, until at the end, you will end up at a higher temperature. That is why adiabatic curve is always steeper than the isothermal lines.
Wow.
Okay, got that? And now we know how to get some relationship in here, even though we don't know how to, we don't want to integrate exactly, but we know in this line, P, V to the gamma stay constant. That's the take-home portion of the adiabatic process. Isn't that cool? All right. So if this is good, then, well, you guys still up for, let's say, one exercise maybe, yeah, before we depart? Sounds good? All right, so let's do some quantitative calculation a little bit, shall we? And then we can call it done, and then we can continue doing more serious calculations later, right? I think it's quite a lot today. Today is like the whole nutshell of first law of thermodynamics is all in here. Right. If you kind of like go back and revise everything and then kind of understand what we are trying to do among these three terms, the U, changing, the heat, and the work, that's it. That's the first law of thermodynamics. All right, try this one, guys. 1 mole of an ideal gas does 3,000 joules of work on the surrounding as it expands. Isothermally, see that? You have to specify the process. Isothermally to a final pressure of 1 atm, and the volume is given to be 25 liters. This is different units altogether. Determine the initial volume and the initial temperature of the gas. All right, try this one, guys. You start to see what kind of problem will pop up, right? It's going to ask you here, ask you there, and then you have to somehow put all those information together and then try to answer something. All right, 1 mole of an ideal gas does 3,000 joules of work. So this one already give W. But because this gas performed the work itself on the surrounding, I can even do better. It's a positive 2, is it 2 or 3? 3, sorry, 3,000. See, it's a positive sign right there. And it's expand isothermally. When you think of isothermal, go back here. This is what it is. See, that's how you use it. is the first law of thermodynamics with extra condition of constant temperature. So with that, heat will be equal to the work, and it's going to be equal to nRT log V final over V initial. See, that's not too bad. We have that in our hands now. Now, your final temperature is given. The volume is 25 liter. The final pressure is 1 atm. They want to figure out what is the initial volume and the initial temperature. How can you figure that out? Very good. Got that? See, there is 1 mole right here. So that's N equal to 1 mole. Hey, John, I have the number of mole. Actually, I know what is the final volume. I know what is the final pressure. I can start by using the equation of states. All right, that is the common initial temperature is the same. Yeah, that's a good start. Initial temperature and the final temperature must be the same. That's for sure. Second, I know N, I know volume, I know pressure. PV equal to nRT. But because I know everything under final temperature, I can put subscript F here, F there. That's fine. And that's it. Pressure is 1 atm. I can turn it into Pascal if I want to. Okay. The volume is in liter. I can turn it into cubic meter, multiply by 1,000. Okay. Oh, whoa, whoa, whoa. No, no, no. Divided. Sorry, guys. That's getting bigger. Sorry. So divided by 1,000, 10 to the negative 3 cubic meter. N is 1. R is always R. And that's it. From this equation, I will be able to figure out what is my final temperature of the gas. And as your friend just said, yeah, definitely it has to be equal to initial temperature because everything is fixed. All right. And with that, I can use all this knowledge and information, plug it back in here. So from the conditions of the isothermal process, W is 3,000 positive. N is 1. R is R. T is known. Or actually, you can say it down. This is just a PFBF. No problem. You can use that. They are the same because that's what we sort of use this to calculate temperature anyway. And then log V final over V initial. But everything is already known. You guys with me? Yeah. This is known, 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 known. You should be able to figure out what should be the initial volumes right there. And that's it. That will give you the final answer. VI equal to and T sub I must be the same as T sub F. Can you fill in the blank? All right, you just work on the details using your calculators at home, all right, at your own time and then everything. But I hope this gives you a sense of what's supposed to happen next week. All right, we are going to go back and forth between first law of thermodynamics. We're going to do equation of state, and we're going to just apply those known processes. And then we're going to build something out of it, maybe like a bigger processes in a PV diagram. And we can even use those to explain an actual working stuff like air conditioner, car engine, and all that stuff. And there are good stuff coming next week for sure. Okay, sounds like a good plan. All right.
Okay.
All right. So if that is a good one, I think it's a good place to stop. And then don't forget to go back and revise what we have been doing today or up until today's lecture and get ready, sort of like get yourself ready for next week adventure. All right. All right, guys. Take care. I'll see you guys next week.